We will talk about hashing as it relates to hash table, which is a specific implementation of a map in this lecture. So the reason why we're talking about this and the reason why hash table is being used so much in computer sciences is because it is a very, very efficient way of implementing a map, okay, this data structure. Because hashing gives us, the hash table gives us an all one operation implementation. So this is both insertion and deletions. And this is a very, very fast operations. Also the lookup, right, of one, almost instant. One thing about hashing is that it uses an array. So it does not use tree, does not use graph, does not use queue stack, none of that stuff. It's basically just using an array. And this array, obviously has, limitations, right? First of all, it gives us a upfront a memory bucket where we can dump information into it to allow for this O1 operation. So just on a very high level, a hash table is a data structure, right? That makes use of this hashing, right, property inside the map that stores unordered items by mapping, right, or hashing each item, right, to a location inside an array. Or sometimes we call it vectors too. And that basically allows us to, this underlying array to keep track of our key value pairs. So hashing generally involves determining array indices directly from the key of the entry being stored and accessed. So sometimes we call these things a hashing function, right? So hashing function, you can think of it as one example is a hashing function that makes use of a modulus, right, operators, or that percentage sign, right? So you see in computer science. So from your intro Java or other intro language course, this right operations operator involves computing the integer remainder when dividing two numbers. So we'll get into the specifics here, but let's move on to the next page here. So this compression function example is what we call hashing function. Okay, this is a hashing function. So it basically involves hashing a number or mapping a number to another set of number that are inside this array. So this is an array of 100 elements here, okay, 100 elements. So the hashing function we're trying to use is modulus. So this involves, let's say if this ID number is this, right? So when you hash it to modulus 100, it gives you basically the number, right? The first, 100 numbers. So whatever that is, 50704 mod 100 is going to give you 4, right? So that way you can map that information to the slot right there, right? So this 4 maps there, right? So it depends on what you have this number is. It could be 5 0, right, 7 14. Well, if this is the case, when you mod it by 100, what you get? 14. So this then goes into the 14 slot, right? So on and so forth. If this is 50000, then it mods to over to 00. So using this compression or very, very simple or commonly used compression function, you can group basically any numbers, any positive numbers to a value within 0, 0 to 99, okay, using a mod 100. So this is just a very common example, right, where you can, shrink or bucketize, right, a large group of values into a bucket. So this employee list of 100, making use of mod 100. So anyway, so this is a compression function or a very, very commonly used hashing function that you see in HashMap. Okay. Now, if you go back to this example, you're going to have a lot of numbers that eventually hashes to the same number, and that's what we call collisions. Collision is inevitable, and this is generally, our biggest pitfall, right? So not a data structure is perfect. So this data structure, even though it gives us O1 in terms of lookup, the biggest issue with hash table is collisions. So collision challenge is always, it's always a problem. So we can devise a number of algorithms to alleviate, right, the collision, potential, as well as if we do get into collisions, how do you manage the duplicated elements to allow for the quickest lookup? So these are, some of the details that we can look into when we're 8.5 hashing function. So we'll talk about that later. Generally, when we're discussing our collision resolution policy, let's just assume that the information that we have inside the object is held inside the info array, right? So this array info has got n number of elements that we have there, and the integer number location is indicated the array hash table size. So not trying to get into too much details here. If you want some details here, you should be able to look up hmap. So this is hashmap.java that is available inside your modules. So in the next couple of slides, we're going to talk about collision resolution. So collision resolution means the ability to resolve the collisions, right? So we have to enforce some policies on our hashing function to avoid, to manage, right, collide keys. So the first thing that we come to mind is what we call linear probing. And as the name implies, linear means, right, one-to-one relationship. And the other one is what we call quadruple, right, or quadratic probing. And then we can talk about later on trying to do towards bucketize the collisions using buckets. So the linear probing one is a very naive way of avoiding conflict. So when you have, this is an example, when you have a list that you already have here, where one is 14001, so on and so forth, and all of a sudden you have to add a key, and this one is 77003, using the same hashing function modding by 100. This 003 is going to mod to, it's going to result in a 3, right? But if you look at the 3 is already occupied. So what you're doing here is you can't just overwrite this. This is because if you replace 5003 with 77003, then you end up with information loss. That's not good, right? Data structure holds information, so you can't do that. So the very logical way of slotting this 77003 downstream is to find the very next, right? The very next available space. So this is a naive way of doing things. As you can see here, eventually you're gonna run into a situation where none of them is available. And the worst case is when you have something all the way on top and then all of a sudden you have to keep jumping all the way to the end, right? So this entire linear probing thing works in the beginning, but later on it becomes more and more of a drudgery to have to find the open slot. So that said, 77003, if you look at the entire list that we have here, it turns out if this one is not available, then the very next one is going to be at slot number 5, right? Slot number 5. So this allows you to basically just make use of whatever is available next. There is no algorithms there. It's simply just doing a lookup, right? Find and search. So as you can see here, even though the compression functions here is very, very fast, it's O1, but the lookup right there, just by looking at, probing into the, the variable slot one after the other, could be O of n here. So this is not very efficient. In fact, this is our biggest pain point, right? Using hash tables whenever there's a collisions here. So this describes the very first type of linear probing algorithms that you can use in conjunction with the key, right? So it's not just hashing the key, right, to a value, but also locating the right spot for it to insert. So this is a combination approach, making use of linear probing. Let's move on to the very next one, which is, actually before that, let's just look at item removal here. Now, this is very, very, this is a very, very, very inefficient way of keeping track of data, right? Just by looking at this. Now, how do you know just by looking at it that this entire 770 is to be removed, or if this null is actually not a value, but it's not a default value, but the actual value that someone dumped in there, right? So you don't know, right? So there needs to be another set of information that is tied to these informations that needs to be attached, right? Or basically saying, what is the metadata associated with this value? So that the easiest metadata is Boolean, right? Saying that this entire value that you insert in there is not a default one, but the actual one. So this is the reason why as a next step, right? If you need to know which elements is supposed to be removed, you keep track of so what we call dirty bits. False meaning this hasn't been overwritten. True means yes, this has been overwritten, right? So on and so forth. So you can see these color additions, but in computer science at runtime, there's no color additions here. So you're gonna have to have some sort of flag, right? That says, hey, this value has been changed, and you can you probably don't want to touch it. If so, you gotta make some indications to it. But otherwise, feel free to touch it. Lots of times, when you have something like this, it's very tricky to remove elements. You gotta make sure when you remove something, that information, is tied to some others that also need to be notified. So this is the reason why searching is complicated. You can immediately hash something, let's say this value into this respective slot. Next time you have to do something like this, you get to the destination, which is 03, but later on you're going to have to keep track of going. But eventually when you remove 77003, you're going to have to see basically O of n, right? O of n to look for its occurrences downstream. So that's what I wanted to say about item removal with this approach. Same thing with what's called quadratic probing. Now this quadratic probing, neither linear probing or quadratic probings are popular in computer science. The quadratic probing is basically saying that instead of finding to the very next available slot, what you want to do is the value added at each step is dependent on how many locations have already been inspected. So there is a extra variable, right, that you're going to have to keep track of. The first time that this value takes place, it adds 1 to the original location. The second time that this same value happens, it adds 4 to the original location. And the third time this happens at 9. So basically what you're doing is you're quadratically spreading the value of these duplicates out from 1 to 4 to 9, and then what's the next one? 16. The one after that, 25, 36. So there is a sense of a distance, right? When something repeats events, like first time it happens is here, and then second time it happens is going to be stored here. The third time it happens is going to be stored here. The first time it happens is going to be stored here. So you can see that the distance, right, between this duplicate kind of just goes up and down. So you can keep track of these things by internally storing a value that is associated with duplicates. As you can see, this allows you to, immediately kind of jump to the required locations once you have this I in place, right? But this also means that, at some point you're going to run out of the bucket, right? The bucket only has 100 elements. Eventually it's going to wrap around. It's like a circular fashions into the next slot, so on and so forth. And at some point, when you have sufficient elements, eventually you're going to get into situations where it's not easy, right, to find the next available spot. You might as well just go through the linear probing approach, looking for the next available slot. So this is a comparison of the two approaches. One uses the linear probing, and the other one uses using the quadratic probing here. So the order insertion is on the left here. And the array is the same, each having a 100 elements sitting in there. The linear approach basically says, let's say, they're basically in order, right? So this is gonna, when you mod this by 100, you get 1, and you get 2 here, and then you get 1 again, right? But because this 1 is already occupied, you can't go there, so you go for the next spot, which is 3, right? So this allows you to kind of linearly grow, right? Linearly grow your bucket. Now, using a quadratic probing here says, if the first one happens, so this is what happens, you insert it. If this is the first time it happens, you insert it. But, right, 4, 3, 2, 0, 1. This is the second time that this 1 happens. When you mop this, right, by 100, you get 100. You get 1, right? So 1, so this is the second time 1 happens, so you're going to have to move So the algorithm says what? I, right, square. So if this is the second time that this 1 happens, what you have is 2 square, and this is going to give you 4. So basically what you need to do is move it down by 4. So you count the number. So this is the first time, second time, third time, and fourth time. So you need to space out this 1 to the 4th, right, locations after the initial locations, right? And the second time this happens, or the third time this happens, you're going to have 3 square, and that is 9, right? So this 9 says that if this is the third time that this happens, like 1 happens, then what you want to do is move all the way down by 9 elements, right? So this is what happens when you have this again, right? This very third time that 1 happens, or the value that modular is creates a modular. This number modular mod 100 gives you a 1. Then this one slots it into the location number 10. So so on and so forth. So this is the comparison between 2, and at some point you're gonna kind of run out of this space, and there's no more. And then simply what happens is it just wraps around to the beginning, and you start counting again. So this is the algorithm associated with quadratic probing versus linear probing. Both are, as you can see, pretty inefficient, because you're gonna have to, if a slot is inserted, what do? And then you move on, right, to the next one. So there needs to be a way of kind of managing the spaces of these elements. So this is not efficient. So a lot of times people, instead of doing that, what we call we come up with what we call the buckets and chaining, right? So this essentially means that what you do is you create a 2-dimensional structures here. So the first dimension is your vertical directions, right? So this vertical directions says you have value 1, you have value 2, value 3, and if there is more than one element associated with this key 1, what you do is you grow your linear list like this, right? So in this case, you have 1 element. You can also have another element that ties to it. Let's say if there are more than 2 occurrences of 1, right? The second one is going to be kind of appended, right, to the next one. This is what we call buckets. So each of these is a bucket. Let me just illustrate it using a different color. So this is a bucket, okay? So you can have another bucket. So basically, if you have 100 elements in there, you can have 100 buckets. Each bucket is a list, right? And another way of saying it is a chain. Each list is a chain. So this allows you to kind of grow this horizontally. If there is more than 1, like I said, this is a list. It doesn't, when I say list, this is just a data structure. You can use an array to represent that list, right? So the underlying implementation is totally up to you. But the idea is that you will grow horizontally for any collided element, to store any collided elements in there. And when you store the collected element, and by that I meant the value, right? The key is always 1, right? In this case, is 1. Or in this case, the key is 3. In this case, key is 5. In this case, key is 99, right? So the value is chained, right? What gets bucketized and chained is your value, right, associated with that key. So this is one very, very common approach. As you can see here, every time you have a key collision, what happens is you're going to have to iterate, right, through your chain from the beginning all the way in, looking for that specific. Let's say if your target is 72101, you're going to have to locate, first of all, using mod 100, the key location. And inside that key location, there's that list that you have to iterate through. So iteration of that list from here to here, there's no easy way out, okay? This is O of n, right? Assuming there's n elements out there. Now, your worst case scenario, this is a very, very unlucky situation, right? Where all of your elements are colliding against each other. So all of the keys are in collision. So in that case, you're gonna have this one linear, right? Basically one linear list, horizontal bucket of n number of elements. So that's the worst case scenario. And obviously, lots of time that don't really happen. That is just a very bad, if that happens, that means your hashing function is really bad, right? You want to change it. But this is the reason why hashing function becomes important. That is the subject of our next chapter's discussions, right? So we're going to spend some time to talk about that. and how you can make your hashing function to produce unique set of keys, right? Unique set of keys. So you don't want to use mod 100, right? This is, I mean, it's just illustrations here, but hopefully this illustrates how we, um, you know, provide conflict resolutions in the policy that we use, or various different policy that we use in the hashing function to deal with collisions inside a hash table, which is a special implementation of map. Okay. All right. So we'll talk about hashing functions in the next sub chapters.